Welcome back to the AIDC debate. This is part 2 of our very first episode. So far, we've covered the truths. Now, let's talk about the trends. All right, Manoj, why don't you kick us off? What are your main trends for 2026?
2026 is going to be an exciting year. We should expect a lot of drama this year, especially when we are actually going through a so-called memory supercycle. So there is already a lot of drama happening in Korea where most of the memory chips are made by SK Hynix or Samsung. And actually the lobbyists or the procurement teams of the large customers, hyperscalers, OEMs and all that are actually camping in Korea. And they are actually negotiating prices and volumes with these memory vendors on a day-to-day basis. It is actually ruthless negotiation. The memory vendors are actually putting in place. They seldom get this chance because the memory is like mostly treated as a commodity, and the prices reaches rock bottom most of the time. But in the super cycle, when there is a big demand supply mismatch, they take all that advantage they have. So the situation is so bad that obviously the demand is actually coming from AI computing. And I will actually get into that at a later time. But the AI servers needs a lot of like memory capacity. And off late, what happened is that the traditional DRAM is actually very low margin business. So memory vendors have actually moving their capacity from the regular DDR5 DRAM to HBM. HBM is a pretty high margin lucrative business. So they want to play in that game. So they move their capacity. And when they move the capacity, the models with thinking capabilities, the reasoning models, deployments scaled up quite dramatically. Most of the models that we are using on a day-to-day basis are reasoning models. And when they use these models, they create a lot of key value cache, basically key and value calculation from the self-attention layers of these transformer models. Keeping this key and value computations in a memory or in a helps in creating better context when you go back to the same conversation and start over that conversation. And it helps to prevent redundant calculations and speeding up inference by allowing the model to reuse the past computation instead of starting it from scratch in all the instances, right? So there is a big demand coming from AI computing for memory. And at the same time, the memory vendors have actually shifted their capacity to HBM and not really the traditional DRAM. So the demand supply mismatch is so bad that we are not really expecting any improvement to happen at least by the mid of next year. The memory prices have actually gone up to 65-70% up compared to 4-5 months ago.
Do you think they can go up further?
I think that it will go up further by a few percentage points as well. Imagine you are actually the Samsung mobile phone business, and your Samsung memory foundry is not really allocating you LPDDR, which is required for your mobile handsets, because there are like high paying like server vendors who are willing to take the same memory at a higher price. So it's actually that bad. So I believe that the PC and the mobile industry will feel the pressure of DRAM shortage quite a lot this year. So far in the first quarter, there is a good inventory buildup with the Taiwanese OEMs and ODMs, but the inventory, whatever they have, will go down in like no time, right? It'll get depleted. That's actually one of the biggest trend that I'm closely monitoring this year. How will that evolve over the next few months? I'm even expecting a situation by maybe the end of second quarter or third quarter. Some of the server OEMs, they may not be able to ship servers because they don't have access to DRAM.
So get your laptops, get your mobile phones now, to be honest, because otherwise there might be a little bit of a...
The price hike is already there. The retail price hike is already happening. Actually, the OEMs, the US OEMs, when you're talking about like Dell or HPE, they started really talking to the Chinese DRAM vendors. That is something which is unheard of. Normally, they either use Micron or like SK Hynix or Samsung for their DRAM, but now they started negotiating and sampling and testing the DRAMs from the Chinese memory vendors to overcome this supply shortage scenario. So there is a lot of drama happening in the DRAM world, and the drama is not so bad in the NAND flash world also. As I mentioned earlier, the key value calculations are pretty chunky, right? So if you are talking about a 70 billion parameter kind of model serving around 100 users simultaneously, the KV cache size could reach up to maybe 16 terabytes just for 100 users. That's actually the kind of like KV cache buildup that we are expecting. So one of the way vendors mitigate this KV cache memory demand is by offloading the KV cache to storage devices. So then we are really talking about NAND flash and like second tier storage, right?
Let me put 16 TBs into perspective. If you are currently listening to us with a MacBook Air, that's 64 MacBook Airs.
That's actually the kind of demand for NAND flash which is in the market currently. And I think most of the NAND vendors are also at their peak production levels, and the capacity is already booked. Even the HDD vendors, right, the Seagates and the Western Digitals of the world, they are almost like sold off their production capacity for the year. So memory and storage is going to create a lot of drama in the computing world this year. Then the rest is not so dramatic. A lot of things we were expecting, like the ramp of rack scale systems with GB200 shipments happening quite a lot now, and the GB300 NVL72 kind of systems ramping up from the end of third quarter last year. This year, we'll see a lot more rack scale systems. We are expecting NVIDIA NVL GB200 plus GB300 plus Vera Rubin, that to account for close to around 60K rack unit this year. And last year, it was close to around 28, 29K.
So more than double.
Yeah. Double is what we are expecting this year, and that's just about NVIDIA's, right? And we have rack scale systems from Amazon for their Trinium 2 systems, and also the new Trinium 3 they started deploying now, and also the Google TPUs, they are also ramping volumes by quite a lot. And even Anthropic alone will consume 1 million TPUs from between this year and early next year. So that itself is a big volume. This is actually out of GCP, out of Google Cloud. I think that's actually the first large customer deployment of TPUs outside of Google. There were some small deployments in the Fluidstack cloud itself, but very few racks. This is going to be one of the largest deployments, yeah.
So there is a bit of a learning curve that I think people are concerned about with the Google TPU infrastructure adoption, because it's very different, right? The racks is double the height. They still use optical networking. But I think that the Fluidstack guys know it very well. So I think that they're going to be the ones operating the Anthropic.
Exactly. So they are actually some ex-Google guys. They know what they're doing. But driving the ecosystem is actually completely a different challenge, right? So when you have to work directly with some of the vendors, like maybe it is Broadcom or like Celestica and all the big supply chain out there, it's not so easy, but I think they'll be able to pull it through.
It does explain, though, why choose Fluidstack, because Fluidstack are aware of how to operate the Google TPU infrastructure. You didn't mention AMD when you mentioned the rack scale designs.
I was talking about the volume runners, then getting into the Helios rack. I think that there will be a lot of like Helios rack shipments, but I'm not really expecting 1 million like AMD MI 450 to be shipped this year. It will be much lower volume, maybe like 500,000 is actually the kind of like volume that we are expecting with the commitments that they already have. And the interesting thing that we could actually expect is like Meta's custom silicon, the first training optimized silicon from Meta. That's also a rack scale system. And we'll see some announcements and also deployments around Meta's custom silicon also this year.
So it might not be in your trends, but I'm curious, do you think that the double width rack is a trend? Because it does look like now there's 2 rack scale designs that are double width.
Yeah. It's all about like optimizing the design, right? For every layer of the design, whether it is like networking and also the thermal power management and the interconnects, etc. And if you look at AWS NVL72 deployment, it's actually in 2 racks, not single rack. So they are actually doing it so that in data centers where you don't have enough power budget per rack, you can actually take up the 2 rack space and also combine the power allocated to 2 places and then like feed it to a single rack. So like there are a lot of advantages, especially from I think the power distribution and like thermal standpoint. Having distributed components inside the rack is also pretty important. Google was actually using wider racks for quite a long time. The TPU racks were pretty wide, like dual. I think it is almost the double size racks. So on the networking side, we are expecting some very interesting technology leaps this year. One is the transition to 1.6 terabit switches. 1.6T Ethernet switch ports will start deployment in data centers this year. Celestica is shipping Broadcom-based switches. Marvell also, and Arista as well. And Cisco also has their own 1.6 terabit switch design. All will start shipping this year. Another exciting thing in the networking world is like we were talking about like co-packaged optics for a long time. And 2026 is going to be the year of co-packaged optics, where we'll see
a long time.
yes.
We've talked about a very long time.
Yes, I think
it's so long that I struggle to believe that 2026 really is the year of co-packaged optics.
Yes, I think co-packaged optics deployments will ramp in data centers this year, especially with NVIDIA shipping their co-packaged optics system, and also Broadcom's co-packaged optics version will also be deployed in data centers this year with some of the hyperscalers. So that is actually the most interesting trend in networking.
All right. So we've talked about memory, we've talked about storage, we've talked about networking, we've talked about compute. Now let's turn our attention to power. So Shen, why don't you give us your power, your cooling, any other physical infrastructure trends that you have right now?
So first of all, I think one thing is in common, that shortage is not only limited to storage and chips, but also exists in all the other infrastructure components. That's actually a very important background. I think one term is going to be the key for this year. It's called energy autonomy, which means a data center will be running on its own energy production rather than taking energy from the grid. So everybody will be pursuing the maximum energy self-sufficiency. And how does that achieve? It can be anything. Gas turbine can be gas gensets, can be even solar panels and wind turbines, and also energy storage systems. So there's a lot of options out there, and it depends on what is available in the region. So the most important thing is to keep the energy supply sufficient and independent and also secure. So if you don't have accessible self-generated energy, it's all right. But nowadays, people tend to build data centers as close as possible to the nearest energy plants or power plant. Even there's, for example, you can build a data center as close to the nuclear plants where you can get a lot of free energy. So that is a number one trend. I think this is going to be accelerated because of the high demand and because of the limitation from energy supply. It does not only exist in the United States. I would say it also exists in many places in Europe and also in Middle East. But I don't see that happening in China yet. But it has been happened in China already at a very small scale. Some of the data centers, which used to be crypto mining sites that utilizes small local hydropower stations.
Actually, when we were looking at the China self-generation, there was quite a few projects that were more like I think proof of concept projects, but there were proof of concept projects with hydro, with solar, at least a few. I know that obviously solar cannot power a data center, but it was to contribute to the power. There was fuel cell proof of concept projects as well. So we actually saw quite a few. If you remember, a few years ago, we were making a list of all of the self-generation projects, and we already saw that there is a very long list.
Yeah, that's correct. So in some of the Western provinces, there are a lot of sustainable energy. For example, in a province called Qinghai, the green energy sufficiency is nearly 100%. But those green energies are on the grid. So if you build data centers there, you're still withdrawing power from the grid. But in some of the places in southwest China, where a lot of small hydro stations exist, you can actually spend not that much money compared to a very big data center. It's nothing. Let's say a few million of US dollars to buy a small hydropower station or your own small crypto mining centers. Nowadays, the crypto mining center is no longer an option. So those guys who used to own a crypto mining data center and who used to own hydropower station, they are now considering selling their facility as data center service. They turn themselves into a colocation player.
I mean, yeah, a lot of the AI neoclouds are opportunists, and they started their world in crypto.
Indeed. So when crypto is not as profitable, they would turn that to data center business because they have the power. They secured their power long time ago before the AI surge. So that's why they have the advantage in this area. But that's a separate story. And my trend two is a higher voltage and less copper. I think this is very clear. And also, I noticed that a couple of days ago, there was a white paper published by NVIDIA, which states that for 1 gigawatt of IT load, they're going to need 500,000 tons of copper. So this surprises everybody. And everybody was so scared of copper shortage. Then NVIDIA said there's a mistake in numbers. So they corrected the numbers. They turned down the number from 500,000 ton to 200 ton, which again brings another very big shock to the copper market and results in a very big drop in the copper price.
It's actually 200,000 tons, right?
Because they state that for each of the megawatts, they need 200 kilograms of copper.
Oh, that is actually 200 kilogram per megawatt.
Per megawatt.
Oh, okay.
We used to do this calculation, and our calculation is about 50 tons per megawatt. There's still a very big gap. Then I read through this paper, I realized that they're only talking about IT. So they're talking about the copper usage in the rack, which I think totally makes sense. But if you look at the entire data center scale, it's about 50 to 60 tons per megawatt, which is still a lot of copper. And copper price is still climbing in the long term. And to save copper, people have the motivation to go for a higher voltage. If you have a higher voltage, if you deliver the same amount of power, then you reduce the current. And if you reduce the current, then the copper is correspondingly safe in the conductor part.
That's much better.
And what comes along with this trend is the DC trend. If you remember Edison and Tesla, they had this kind of AC-DC debates, and eventually Edison won this game. That's why everybody has AC at home. But now I think in the AC-DC debates, in data center of nowadays, Tesla would win. So DC is going to be the next step. So we are not talking about the DC distribution in the server, but we're talking about DC distribution across the whole data center.
So for our non-technical audience, we're not talking about the AC, the air conditioning unit that you have in your house. We're talking about ways of delivering current. Shane, can you just elaborate, in just 2 sentences, what is AC and what is DC?
Sure. AC is alternative currents. It's like the normal 50 hertz or 60 hertz electricity you use at home. And DC is direct currents. It's like the batteries that we use in our small handheld devices.
And the EV chargers.
Of course, in the EV charger as well. The reason is for AC, why it's easier, because our generators and directly produces AC current, because it's a rotating process. So that's why it's a lot easier to get AC and easy to transmit in a long distance. But in the data center, the reason why we would use a DC is because, first of all the IT and components, they can only digest the DC. On the motherboard, your chips and your memories, they all digest the DC. One way or another, at certain points, your AC has to be transferred to DC to feed those IT components. And also, if you use a lot of batteries in your data center, you're going to use DC at certain points. For example, when we have our UPS, uninterruptible power supply unit, if you have a UPS in your data center, there's a battery in the UPS, and this battery is connected to a DC part. Because what UPS does is they convert AC to DC and connect that DC to a battery, and again, reverse that DC back to AC. So since we have so many AC-DC, DC-AC conversions, why don't we just use DC?
So about 10 years ago, Meta published this paper, and actually it should be said the cloud service providers are now proficient in using DC, but about 10 years ago, Meta published this white paper saying that they were able to reap a huge amount of benefits by turning to DC. And it's something Shane and I have talked a lot about on stage, but it is something that we're able to also provide you with some more feedback. So if someone wants to know more about the AC and DC power distribution in data center, leave us a comment and we will get back to you.
Sure. So all the trends are connected. My third trend is also connected to DC. Batteries. I'm not talking about the batteries for UPS. I'm talking about the batteries for the IT rack, which is called the BBU, battery backup unit, promoted by the OCP community. And also on another level, there's another device called BESS, Battery Energy Storage System, which is a large-scale battery storage pool. This one used to be used in grid sites. For example, if a power plant is generating power all the day and it lacks consumption during the night, what it does is that they will store the extra energy into the batteries and release it when it's needed in the daytime. It's going to be for the very first time in data centers at scale. So this will generate a new 3-layer structure for power backup. First level is CBU, a capacitor backup unit, which is in the rack or next to the rack, handling milliseconds of backup. It's just a big array of capacitors. And second layer is BBU. It's also next to the rack, and it's taking care of like a few seconds of backup. On the third layer, you have BSS or BESS. It's a very big battery pool, like in the containers. It can hold the entire data center for 1 hour or 2 hours or even longer. So this is the energy storage, and it could be better utilized if you connect it with a microgrid. So these all 3 trends are connected.
All right. Tell us what it is, the cooling one. And I think the cooling trends will wrap us up for the day.
It can be a little bit technical because in cooling, we don't see a very big structural change because we have already seen it last year. That's the surge demand of liquid cooling. Since 2024, liquid cooling becomes a very popular topic, and 2025 actually is like the boosting year. The most important trend is that two-phase direct chip is gaining more attraction. This is a quite significant trend because you see companies like Accenture is getting orders and getting invested, and some other companies are also announcing, for example, M&As or new orders or new clients. This tells me that a lot of companies are preparing for another alternative of liquid cooling, which is two-phase.
Why do you think they're preparing specifically now?
It's because of pressure of the market. So it's a rapid growth of one-phase direct chip and this pace of IT upgrades had a lot of pressure on our cooling manufacturers, right? As a cooling manufacturer in the past 2 years, when you see your customers switching to liquid cooling, when you see the IT equipment vendors are actually selling super high density racks, you'll be nervous. You're thinking that, can I catch that trend? So now I think there's another wave of pressure. They are worried that maybe in 2 years, this thing will happen again and the IT power density would increase exponentially and people are flooding into the two-phase direct-to-chip markets. So that's why most of the vendors, they don't want to miss the second trend, even if they catch the first trend. So they want to be part of the next high growth new opportunity market, which is two-phase direct-to-chip. It is secure and it is pretty good for some of the applications. That's why I think in this year we'll be seeing some bigger deployment.
And it would make sense then why specifically invest in some of the existing knowledge bases, right? Because those companies that do two-phase now, they're not just a company that makes product. They also are a place where there is knowledge that's been accumulated. It could have been accumulated through experimentation, through trial and error. But the point is they already have technical knowledge that's been amassed. And by working with them, you don't have to find your own learnings from scratch and you accelerate your knowledge gain. So I think that might be one of the reasons why.
Definitely. So I think for one-phase direct-to-chip, the problem may be you need to have access to a pump supply. You need to optimize your supply chain. But for two-phase, the most important thing is knowledge, because two-phase direct-to-chip is a very dynamic and has much more parameters than single-phase direct-to-chip. It's a highly complicated system and has very different challenges and very different advantages. So technology base, knowledge base is the most important property here. My next trend is still going to be about cold plates in single phase. So I think you'll be seeing some new designs. In the past, we have very simple flow channel designs for cold plates, and it is working for the 1 kilowatt chip. But nowadays, we're entering in the next stage of power density, and a lot of new chips will be rolled out in the next couple of years. So I think highly optimized flow channels will be happening in the single phase cold plates. And then the second thing I want to say is that the microfluid cold plate is going to be embedded with the metal cap on the chip.
So it's not going to be going through next to the transistors. You think it's going to actually be outside of the package?
That's correct. So there could be potentially three approaches. One is that you build the microchannels in the silicon, which I don't think is going to be happening because of the pressure is super high. Your silicon cannot sustain that kind of pressure. And the second approach is that you do the microchannel between the silicon and the metal cap. I also don't think that is happening because you have two different materials. You have to bond those two materials together, which creates a lot of risks. And the third part is most likely to happen is you build your microchannels in the metal cap.
And it's not too disruptive.
I think that you are simply combining the cold plates, the tin material, and the metal cap into one. So this is high efficiency, it's secure enough, and you get rid of a few different thermal interfaces.
So with this, I want to say thank you for joining the first episode of the AIDC debate. For us, we did go quite a bit technical in part 2, and we think it was important that we can cover both the business and the engineering side of the house and to really show you what is happening under the hood of the data center. The topic of our next podcast will be the death of the metaverse. And on that bombshell, we will see you all very soon. Thank you so much for listening to the AIDC debate.